In section 3.6, calculations with balanced chemical equations, we're going to take a look at a fundamental type of calculation done in chemistry. It's a powerful tool that we can use to make predictions and to efficiently produce chemicals that we want to. So we're going to take a look at an example here. Moles of reactants and products using a reaction of carbon monoxide with molecular oxygen to form carbon dioxide. So the balanced equation, if you recall, we need to balance equations when we do calculations. The balanced equation is 2CO in gaseous form plus O2 in gaseous form to form 2CO2 in gaseous form. Let's check the balancing. On the reactant side, the left side, there are 2 carbons. And on the right side, the product side, there are also 2 carbons. Now let's check the oxygen. On the left side, there are 2 oxygens for the carbon monoxide, but there's also 2 oxygens for the molecular oxygen, O2. So that's a total of 4 oxygens. On the right side, there is 2 CO2, so that would be 4 oxygens. 2 times 2 is 4. So chemical equation is balanced. A picture is shown above the balanced equation to show us how that works physically. There are 2 carbon monoxide molecules. Remember, the carbon is black and the oxygen is red, so there's 2 carbon monoxide molecules reacting with 1 oxygen molecule to form 2 carbon dioxide molecules, 2 CO2s. So there's our balanced equation. We're going to use that balanced equation in this section and the next. So let's take a look at the example here. It says here that 2 moles of CO are equivalent to 2 moles of CO2. Now, we have to be careful about our wording here. What we mean by that is that in this reaction, 2 moles of carbon monoxide, if they react fully, they're all reacting, all of those 2 moles are reacting, we will get 2 moles of carbon dioxide from that. Okay? There's a relationship which is called a stoichiometric relationship. Stoichiometric just means measuring elements. The stoichiometric relationships is between substances in a chemical equation. So in the balanced equation, 2CO plus O2 to form 2CO2, 2 molecules of CO are reacting with 1 molecule of O2 to form 2 molecules of CO2. But another way of looking at it is to say this. What if I had 2 dozen molecules of CO? 2 dozen molecules, 24, would react with 1 dozen, 12, molecules of O2 to form 2 dozen molecules of CO2, 24, right? So it'd be 24 plus 12 gives us 24. The ratios are what the balanced equation gives us. 2 to 1 to 2, going from reactant to product, is the same as 24 to 12 to 24. Or, if we wanted to, we could do it in factors of 100. We could say 200 reacts with 100 to give us 200. Right? We're just scaling up how much we have. 2 million plus a million gives us 2 million. Or 2 trillion plus a trillion gives us 2 trillion. The ratio is the same in each of those cases. So what we're going to do is we're going to use the mole ratio. And the reason the mole is useful is because back in the previous section we learned, back in 3.4, that moles can be converted to grams by using the molar mass. So if you know the mass of something and you know its molar mass, you can find out how many moles. Or the reverse of that is if you know the number of moles and you know the molar mass, you can find the mass. So we're going to use that relationship here. So it's convenient for us to say 2 moles of CO is equivalent to 2 moles of CO2. Now the assumption there is that the CO is reacting completely, 100% of it, to form the CO2. If only half of it reacted, we would only get half as much CO2. But we're assuming that it's all reacting. So 2 moles of CO is equivalent to 2 moles of CO2, a 2-to-2 ratio, which is, of course, the same as 1-to-1. Notice how these are written as ratios now, and this is done purely for dimensional analysis method. 2 moles of CO divided by 2 moles of CO2. That's a ratio, as in if you said something like 12 inches divided by 1 foot. Or you could write 1 foot divided by 12 inches. We do the same thing with the moles. 2-to-2 is the same as 1-to-1. That's perfectly fine. But we could also write it as the reciprocal. The ratio could be written as the reciprocal. 2 moles of CO2 divided by 2 moles of CO, right? 1 foot divided by 12 inches. We're just flipping over, taking the reciprocal of that ratio. Again, 2-to-2 is the same as 1-to-1. These conversion factors enable us to determine how many moles of CO2 will be produced. So let's take a look at a numerical question. Consider the complete reaction of 3.82 moles of CO to form CO2. So someone tells us we have 3.82 moles of CO, and it's going to form CO2. How many moles of CO2 could you produce? Well, we're going to use that ratio. Here's how we go about it. We know that 3.82 moles of CO is reacting. And we know that in this reaction, we form 1 mole of CO2 for every 1 mole of CO. Now, perfectly fine to put 2 moles of CO2 divided by 2 moles of CO. That would be fine too. It gives you the same answer. What happens is dimensional analysis works to our advantage here. When we take the 3.82 moles of CO and multiply it by that ratio, the moles of CO cancel, and we're left with moles of CO2. So that tells us how many moles of CO2. If you do the arithmetic, 3.82 times 1 over 1 is 3.82, and we learn that in this particular example, we will form 3.82 moles of CO2. Okay? You can also relate it to the other reactant, which is O2. So again, we're given that 3.82 moles of CO is reacting. How many moles of O2 will react? Well, 1 mole of O2 reacts for every 2 moles of CO. Where did I get that ratio? That came from the balanced equation. We come back to the balanced equation here. It's 2 moles of CO for every 1 mole of O2. So this also allows us to predict how many moles of O2 will react. Well, let's take a look. 3.82 moles of CO times 1/2. Why 1/2? Because in the balanced equation, there's 1 mole of O2 that reacts for every 2 moles of CO. So when you take that ratio, 1/2, and multiply it by 3.82, you get 1.91 moles of O2. Notice the dimensional analysis. The moles of CO are canceled. There's our answer. We've now learned that 3.82 moles of CO2 will be produced and 1.91 moles of O2 will react. This allows us to understand more about what's happening, at least the amounts of what's happening in this particular reaction. So let's take a look at an example, 3.10. Urea, for those of you that are biology majors, urea is an important molecule. Urea has a chemical formula of 2 NH2. So it's written in the following way. NH2 parentheses 2. That means there's 2 of the NH2s attached to a CO. It's all one molecule, NH22CO. The square brackets are there because the author is trying to tell you that's the formula for urea. Okay, so it's a little awkward here. There's parentheses, and then there's brackets. The formula would be written with the parentheses, but not the brackets. It's a byproduct of protein metabolism. When proteins are broken down in the body, one of the waste products is urea. Urea is formed essentially as a way for the body to get rid of ammonia. Ammonia is a really nasty chemical in the body. It's toxic, NH3. So when proteins break down, ammonia can be formed. So converting it to urea is a way for the body to safely remove the toxic ammonia. Urea can be synthesized in a laboratory by the combination of ammonia, NH3, and carbon dioxide, CO2, according to the equation. Now, even though the pictures are shown here of the molecules, That's not what you're going to be doing in most general chemistry courses. In most general chemistry courses, you're going to be using the chemical equation with the formulas. So you got to get used to that. But it's shown here just so that you can see it. Okay. All right, so let's look at the balanced equation. Notice it is balanced. 2NH3 gas plus CO2 gas forms NH2 2CO aqueous. Aqueous means dissolved in water, plus H2O liquid. It's an example of what's called a condensation reaction. Water is formed in this reaction as condensation. So essentially the ammonia reacts with carbon dioxide in the laboratory to form urea and water. Okay? So it says here, calculate the amount of urea that will be produced by the complete reaction of 5.25 moles of ammonia. In part B, we're asked to determine the stoichiometric amount of carbon dioxide required to react with the 5.25 moles of ammonia. In a sense, this example problem is helping you to practice interpreting language in chemical reactions. So you're going to see a lot of terms here that are essentially asking you calculate something using these words. This example is just like the one we just looked at with the carbon monoxide, oxygen, and carbon dioxide. We're told that 5.25 moles of ammonia reacts, all of it. So how many moles of carbon dioxide will react and how many moles of urea will be produced? Nothing asked about the water. We could also ask about the water, but we're not going to in this example. So how do we go about this? You take the information you're given, the numerical value, that's the given piece of information, which is 5.25 moles of ammonia. You then ask yourself, well, what do we want to know first? We want to know the amount of urea. Well, urea is the product. The balanced equation says that there's 1 mole of urea formed for every 2 moles of ammonia that reacts. So the ratio is 1 to 2. So that means that if 5.25 moles of ammonia reacts, the amount of urea is going to be that amount, 5.25, times 1/2. 1 mole of urea divided by 2 moles of ammonia. Where's the 1 come from? It comes from the balanced equation. Even though we do not explicitly write a 1 in front of the urea, if the formula has no number in front of it, we assume the number is a 1. So look at these conversion factors, as they call them. These mole ratios, sometimes they're called. 1 mole of urea for every 2 moles of ammonia, the one on the right. So if we, going back to the solution, down to the solution here, if we take a look at 5.25 moles of ammonia and multiply it by that 1/2, that tells us we will have 2.63 moles of urea. Coming back to the carbon dioxide required. The ratio is 2 moles of ammonia for every 1 mole of carbon dioxide, or 1 mole of carbon dioxide for every 2 moles of ammonia. Come back to the balanced equation. Where do those numbers come from? 2 and a 1 on the reactant side, 2 moles of ammonia for every 1 mole of CO2. So we're going to use this ratio on the right, 1 mole of CO2 for every 2 moles of NH3, because we want to know the number of moles of CO2. So in part B, moles of CO2 required, 5.25 moles of ammonia times 1/2, and that gives us 2.63 moles of CO2. So our analysis here would say that if 5.25 moles of ammonia reacts, the amount of CO2 that will react is half of that, 2.63, and the amount of urea that will be formed is also half that at 2.63 moles. The next step is to start converting these into grams, because we do not have devices that measure moles. We have devices that measure mass, balances, and scales. So try the practice problem A and B, but let's move on into masses of reactants and products. Sample problem 3.11 just throws all of this mass calculation in here. There's no real discussion of it till you get to this problem. So this sample problem really is what's being used to teach you how to do this, okay? Give you some practice for it. So I'm going to go over this problem here, sample 311. Nitrous oxide, which has the formula N2O, is also known as laughing gas. Dentists sometimes use it, right? It's commonly used as an anesthetic in dentistry. It is manufactured by heating ammonium nitrate. Ammonium nitrate has the chemical formula NH4NO3. So the solid ammonium nitrate is heated. The little triangle above the reaction arrow means that you're heating the reactants. In this case, there's only one reactant. It decomposes. Decomposes means it breaks up into N2O, which is a gas, that's the nitrous oxide, and 2H2O, also is a gas because it's hot. Calculate the mass of ammonium nitrate that must be heated in order to produce 10.0 grams of nitrous oxide, and then in part B, determine the corresponding mass of water produced in the reaction. Okay, so in this example, what we're going to do is we're going to combine the calculations we learned back in 3.4. If I gave you the mass of something, you could convert it into moles by using its molar mass. If you had the moles of something, you could convert that into the mass by using its molar mass. We're doing that here, even though it doesn't tell you to do that yet, and we're using the mole ratio that we just learned in the previous example, 3.10. So the strategy is given here. Essentially what you'll do is you'll say, look, we're forming 10.0 grams of N2O. Convert that to moles by using its molar mass. Once you've got the moles, then you can use these mole ratios to figure out the moles of the substance you're interested in, and then use the molar mass of that substance to convert it to grams. So that's essentially the strategy. It's 3 steps you're doing, a 4th if you consider the fact that you're calculating the molar mass. So you really got to be organized in these problems. You're going to go step, 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 step. I highly recommend with this type of problem that you have a whole sheet of paper. You write down the numbers and the chemical formulas of everything at the beginning that are given, the ones that are given. In this case, it's N2O. And then step by step, show yourself how you're doing this calculation so that you can see what you're doing. Don't just grasp at the numbers and try to write numbers down and busily go through stuff. You want to be very methodical about this. Imagine this. Imagine that you're more advanced and you're now finished general chemistry, and you're going to teach this to a high school student. Your goal is to teach a high school student how to do sample problem 3.11. That's what you want to be able to do. So here's the setup coming down here. The molar masses are as follows. So notice the author just wrote out the molar masses, not showing you how to do it. As you do these problems, you probably want to show how to do it. On an exam, I would expect you to be able to show how to do it if you were taking the next course. So NH4NO3, 80.05 grams per mole. How did that get about? Nitrogen, 4 hydrogens, another nitrogen, and 3 oxygens. Add those molar masses and you get 80.05. N2O, 44.02 grams per mole. Where'd that come from? 2 nitrogens, 1 oxygen. You're looking those up in the periodic table or some other table. Water, 18.02, 2 hydrogens, and 1 oxygen. You're going to use those molar masses in these calculations. So when we get down to the solution, 10 grams of N2O divided by its molar mass, that'll tell you how many moles of N2O. Now, the first material that we're interested in is the ammonium nitrate, the reactant. So what's going on here? We're taking the 0.227 moles of N2O that is in the 10 grams of N2O, and then we're using the molar ratio to find out how many moles of NH4NO3 are going to have to decompose in order to make the 10 grams of N2O. So the ratio from the balanced equation is 1 to 1. 1 mole of NH4NO3 reacts to form 1 mole of N2O. So the number doesn't change. It's still 0.227. It's just that now it's NH4NO3 because we use that ratio. Now, what we can do is we can convert that into grams. The question was how many grams, or what's the mass? When you hear grams or mass, they mean the same thing. Grams is the unit, mass is the quantity, but we will change back and forth. This many grams or that mass, it means the same thing. 0.227 moles of NH4NO3 times the molar mass of NH4NO3 gives you the grams of NH4NO3, which is 18.2 grams. Okay? So 3 steps in there, not even including that you're adding these numbers to get the molar masses. It's really 5 steps that you're doing here just for that first part. Okay, 18.2 grams of NH4NO3 is going to be produced. If you are struggling on the dividing by molar mass or multiplying by molar mass to get grams or moles, go back to section 3.4, rework those problems mass to moles, moles to mass. These are now steps in more complicated problems, so you've got to have those down. In part B, now we're going to do the water. We're going to look at the water. So notice, the more organized you are, the faster this could be. We know that from an earlier step in part A that there's 0.227 moles of N2O that was produced. Well, you got the moles. So now let's use the molar ratio between water and N2O, nitrous oxide. There's 2 moles of water formed for every 1 mole of N2O, 2 to 1. So if you take the 0.227 moles of N2O and multiply that by 2 over 1, you get 0.454 moles of water. So that tells us how many moles of water was produced. Convert that to grams. When you have moles of something, you multiply it by its molar mass, and that will give you the mass of that something. So for water, it's 18.02 grams per mole. So multiplying that by 0.454, you get 8.18 grams of water. So now we have 2 results. 10.0 grams of N2O was produced, 8.18 grams of water was produced. If you add those 2 together, you get 18.18 grams. However, the N2O was only 0.0, not 0.00, so it only went out 1 digit past the decimal point. So adding those 2 and rounding, you get 18.2. 18.18 rounds to 18.2. That's exactly the amount of ammonium nitrate that had to be heated. And the reason for that is that if all the ammonium nitrate is being reacted and converted into N2O and water, the amount of N2O and water, the mass of that should be the same as the mass of NH4NO3, ammonium nitrate, that was decomposed. Mass balance. The mass of the product should equal the mass of the reactants in this example. Okay. That's given in the discussed there in the think about it part right there. So in that section, that's a little tricky because they just throw the problem at you. So if you weren't able to do that problem without, really hearing something about it, that's perfectly fine, because really they're combining section 3.4 and 3.6 into that type of problem. But that is an essential type of problem, so you got to practice that. So practice problem A, B, you want to work on those for sure. You want to do the checkpoints, 3.6.1, which is a mole type calculation, and then 3.6.2, which is a mass calculation. It would be nice if they gave a few more examples of this type of problem, because this is really an important type of problem. You want to work on these as much as you can. So it'll be in the ALEX as well, so you'll be working on examples in there. So you'll have hopefully a lot of practice. Let me know if you need more practice on these. I can certainly get you more problems. The syllabus does have some end of chapter problems you can try for this section 3.6. The last section we're going to cover in the chapter and in the book is 3.7, so we'll discuss that in the next video.